All right, so let's look at the chain rule and some trig derivatives. If you don't know your trig derivatives yet, there they are. I am not going to spend any time going over it. Maybe just pause the screen or pause the video, write those down real quick because we're about to do the chain rule. And the chain rule is used for a situation where you have the composition of two or more functions. So we're not necessarily multiplying two functions or dividing them, but you are putting one function inside the other. And this is your generic textbook definition of the chain rule, where you have a function inside. So this is f of g of x, not f times g. And in that case, you start on the outside and you actually do the outside function first. You do the derivative of f. Notice you leave g completely alone. The first pass of the derivative does not change the inside, but after you do the derivative of the f, then you multiply by the derivative of whatever is inside that f function. Now, looking at math definitions is very confusing, so let's look at a few real examples and maybe it'll make a little bit more sense then. So when you're looking at something, if you think it's a chain rule, what you want to do is ignore whatever is inside. So in this case, for number one, I see all of this stuff inside parentheses and it's all being raised to the sixth power. And so when I'm looking at this function for number one, the first thing I'm seeing is not all of this stuff, I'm just seeing x to the sixth, and I'm ignoring the fact that the inside is kind of ugly. And so if I were to do the derivative of x to the sixth, that would be 6x to the fifth. And so that's exactly what we're going to do for number one. We're just going to ignore the fact that in the place of an x, we have a different polynomial or a different function. So my derivative, number one, we're ignoring the inside. We're going to bring the 6 down, leave the inside alone. We don't touch that inside function on the first pass. And now it's to the fifth power. And now that I've completely finished, I've done stuff to the fifth power, that's done. Now I look on the inside and we will multiply by the derivative of whatever is inside. So now I'm going to multiply by a 12x cubed plus 2x. And do watch your parentheses. You have to get all of that in parentheses. So there is your chain rule for number one. Number two, again, you're looking for something inside of something, and here we have 5x minus x cubed inside the square root. And so I'm going to start by rewriting this as 5x minus x cubed to the 1/2 power. That way I see the parentheses, I see an inside and what's happening to that inside. And the derivative of number two is going to be almost identical to our approach for number one, where instead of seeing ugly stuff to the 1/2, I'm going to look at it as just x to the 1/2, and the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And in this case, in the place of the x, we have 5x minus x cubed. So I'm going to start by bringing down the 1/2. I'm going to leave the x, the inside, alone. And then I'll subtract 1 from the exponent. That takes care of my outside function. My outside function was stuff to the 1/2. Now I look inside and I'm going to multiply by the derivative of that inside function, which will be 5 minus 3x squared. And all of this is the derivative. All of that is the derivative. So start on the outside and slowly peel your way in until you've worked the derivative of the inside layer. Number three, we have an exponential function. And exponential functions do tend to cause a little bit of anxiety. You sometimes, when you have an e to the x function with derivatives, you don't have parentheses around that exponent. And without the parentheses, it's a little bit harder to identify the inside, because a lot of times with chain rule, you're looking for parentheses, which is what happened on numbers 1 and 2. We had parentheses to the 6. We had stuff inside the radical, so the inside was a lot easier to see. Without parentheses around an exponent, sometimes people don't recognize that the exponent is the inside. And so I'm looking at this and I'm ignoring the fact that my exponent is ugly, and I'm going to pretend that this is just e to the x. And I like that because the derivative of e to the x is just e to the x. And again, just like before, I'm ignoring the fact that in the place of the x, we have an uglier function. We're going to ignore that for the first pass. So my first pass, y prime. We copy it, it's e to the x. And so e to the x is my first pass. So I just did the derivative of the exponential piece. So I've now differentiated the e part. Now that I've done that, I'm going to look inside, and we need to multiply that whole thing by the derivative of the exponent, which would just be 3x squared. So there's your derivative for number 3. In the case of an exponential, I usually will not put the exponent's derivative on the right side like this. I prefer to put it in front, and 2 reasons. 1, I just think aesthetically it looks better. 2, it makes it eliminates a possible reader error where the person grading or reading your work may accidentally think that your 3x squared is part of the exponent. And so we want to eliminate that possible misreading by putting that 3x squared in front of the e to the x. So it's painfully obvious that x cubed plus 1 is all there is in the exponent of your answer. So number 4, we have a trig function, and inside the sign we have an ugly square root of x. It's not sine x, there's something else replacing that x. And so when I do the first derivative, I'm going to do the derivative as if it were just sine x. And again, we're ignoring the fact that the inside is not an x. It's a little bit uglier. So I'm going to do the derivative by doing the derivative of sine first. That's the outside function. The derivative of sine is cosine. We will leave the square root of x alone. Leave the square root of x alone, and that has finished off the derivative of the the outside function. Now I'll look inside, and I see a square root of x, and the derivative of the square root of x. But out here, the derivative of the square root of x is 1/2 x to the negative 1/2. And after this example, I really don't like having 1/2 x to the negative 1/2. That is the same thing. So let me copy down the cosine part. That is the same thing as 1/2 square root of x. And that looks a lot better too. There's nothing wrong with 1/2 x and negative 1/2. I just prefer that way of writing it. So from now on, if I see a square root function, I'm going to do the derivative as 1/2 root x. But this is your whole derivative for number 4. Let's see, I think I have 3 more. Trig. Okay, so cosine squared. This is one of the sneaky ones, especially if you are new to the chain rule, because people don't necessarily see the inside. But if you have cosine squared, you need to know that that is the exact same thing as cosine of x, all squared. So if it's cosine squared of x, it's the exact same thing as this. And now number 5 is going to differentiate very similarly to the way we did numbers 1 and 2, where we had stuff to the 6, we had stuff to the 1/2. This time we have, whoops, too far. We have stuff to the 2nd power. And so I'm looking at this, my inside is cosine, the outside is the exponent of 2, and so my big function that I start with is y equals x squared, and the derivative of that is 2x. And so we're going to do that, only we're going to leave the x as cosine. And so this derivative, I'm going to bring the 2 down, leave the cosine alone, because that's the derivative of x squared. It's 2x, here it's 2 cosine x. So I've now done the exponent part. Then I need to multiply by the derivative of the inside, and the derivative of cosine is negative sine x. I'm going to move that negative in front and maybe reorder it. Sine looks better before the cosine, so negative 2 sine x cosine x. And if you're being really crazy and you just want to show off your knowledge of trig identities, you might recognize that as the double angle identity for sine 2x. Of course, any of these are acceptable. If you are in AP Calculus and this shows up as a multiple choice question, it is very possible that the options are in some double angle format. So just one of the identities you might need to recognize. See number 6, this one's getting kind of wonky. I see a square root of a tangent, and then I see inside the tangent other stuff. This one's going to actually be a layered chain rule. So we have tangent, come on, there it is. So we have tangent x cubed plus 9 all to the 1/2 power. And so I'm looking at that, and yes, there's a lot of ugliness on the inside, but we're going to 100% ignore the ugliness and think only about stuff to the 1/2 power, and the derivative of stuff to the 1/2 power is 1/2 square root of x, right? And so when I differentiate that, I'm now going to write that as y prime equals 1/2 square root of x, only in the place of x, we have the tangent of the x cubed plus 9. Okay, so there's the first pass at my derivative, and that just knocked out the exponent of 1/2. Now I look on the inside, and it's like I have a whole new problem. So my whole new problem now is I've got to do the derivative of y equals the tangent of x cubed plus 9. Because now that I've done this, I'm going to have to multiply. I'm going to chain rule, and I'm going to multiply by the derivative of the inside. And so I'm looking at that. That is tangent of stuff. And here we have, we have stuff to ignore. This is a chain inside a chain. So it's the square root of stuff, and then inside I have tangent of stuff. So I'm going to start by doing the derivative of the tangent, and the derivative of tangent is secant squared. And that knocks out the tangent, and I only do one layer at a time. I'm not going to touch the x cubed plus 9. I'm going to leave x cubed plus 9 alone. And now that I've done the 1/2 and I've done the tangent, now I peek one layer further in, and my deepest inside part is x cubed plus 9, and the derivative of x cubed plus 9 is 3x squared, and that finally knocks out the innermost part of this chain rule. Now, I'm going to rewrite this, simplify it a little bit. There we go. Stop doing that. Whatever. Okay. So if it's 1/stuff times all that, it just looks a little bit better. I'm going to move this secant squared x cubed plus 9 times 3x squared. I'm going to put the 3x squared in front. I said secant cubed. I don't know what I said. Secant squared of x cubed plus 9 over 2 square root of tangent of x cubed plus 9. And that was a booger. That was a chain inside a chain. And that is when derivatives really start to get hazy and weird, is when they start to layer and stack on top of each other. One more problem. Number 7 is 3 to the sine of x to the 5th. And this one also is going to have a couple of layers to it. The first layer, it's like that e to the x example we had earlier. Instead of 3 to the x, it's 3 to a bunch of garbage. And so my first pass at the derivative is going to be to do the derivative of 3 to the x. And the derivative of those exponential functions, it's 3 to the x. It's not a base of e, it's a base of 3, so we need to multiply by the natural log of 3. And that would be the first pass of the derivative here. So y prime is 3 to the sine of x to the 5th times the natural log of 3. Okay, and all of that was just the derivative of the 3 part, so the 3 to the stuff. But then, now that I've knocked that out, I look inside that, and inside that I see a sine of x to the 5th, and this itself is a chain rule, because inside the sine, I have an x to the 5th. So instead of sine x, it's sine of stuff. I'm going to start by doing the derivative of the sine, and the derivative of sine is cosine. And so that does the derivative of the sine part, but again, we don't touch the inside. You only do one little layer at a time. So I left the x to the 5th alone. So I did 3 to the stuff, ln 3, then the derivative of sine is cosine. I left the x to the 5th alone. Now I finally finish up. I've done everything except this innermost layer, and the derivative of x to the 5th will be 5x to the 4th. And that finishes this problem. And that's so ugly, I'm not even going to try to rearrange it. We'll just stop and let that be. So there is the chain rule, a few examples getting hazier and hazier as we work to the end. Hopefully that made a little bit of sense.